So this video illustrates the results of my project on Perlin noise. So for the first part of my project, I did a comparison of different noise functions, and the results of that comparison is illustrated here. So you can see the window is split into 12 different viewports, with each viewport containing a different noise function. So I'll explain each of them now. So in the first row, each square illustrates classic two-dimensional Perlin noise, and each square, so in each subsequent square, the frequency is double that of the previous square, while the amplitude is half that of the previous square. So, for example, the first square here has the lowest frequency, then here we double the frequency, half the amplitude, double the frequency again and half the amplitude, and again we've doubled the frequency and half the amplitude. And you can see that as the frequency increases and the amplitude decreases, the noise becomes a lot finer. Then in the middle row, we illustrate what Perlin called 1/f noise, or which is also known as fractal Brownian motion. So when two different noise functions share a ratio of 2:1, it's called an octave. So fractal Brownian motion, or 1/f noise, is created by summing different noise functions, or like summing different octaves of noise functions, where each time we double the frequency and half the amplitude. So the first square here in the middle row is just 1/f noise, where we summed over one octave. So it's essentially the same as this square here. Then this second square here is 1/f noise created by summing over two octaves. So it's actually the sum of the first two squares on the top row. Similarly, this square here is 1/f noise constructed by summing over three octaves. So it's actually the sum of the first three squares on the top row. And finally, the fourth square here is created by summing over four octaves. So it's actually what we get when we sum all four squares in the top row. We can see that as we increase the number of octaves, while the overall sort of structure stays the same, the level of detail increases as we add more octaves. So here in the final 1/f noise, its overall shape is determined by the lowest frequency function here, whereas as we added in these octaves here, the level of detail increased. Then the bottom row, we've got a mix of different things. So the first square on the bottom row is what Perlin in his paper called turbulence. So turbulence is also created by summing different octaves of noise functions. However, we take the absolute value of the noise functions, and this gives it sort of this veiny effect that we can see here. Okay, so all the functions I've described so far have been two-dimensional, whereas the last three squares here are all constructed using three-dimensional noise functions, where we have two spatial dimensions and a third time dimension. And basically the effect of using the third time dimension is it causes the result to change with time, and we get this sort of animated effect. So this first square here is classic two-dimensional Perlin noise with a third time dimension added in. So it's essentially this first square here, but made to vary over time. Then this tile here is 1/f noise, or fractal Brownian motion, summed over four octaves with a time dimension added in. So it is essentially this tile here with a third time dimension added in to make it vary with time. And finally, the last square we have here is turbulence with a time dimension added in. So it is essentially this square here with the time dimension added to make it vary over time. So here we can see the output of the second part of my project on Perlin noise. So for this part, I created 4 different textures using the noise functions that I just described in the first part of the video. And then I've illustrated these different textures on the 4 teapots that we can see here. So the first texture created is wood. So we have the wooden teapot here. And this wood effect is created using a 3-dimensional 1 over f noise or fractal Brownian motion function. The second teapot that we can see here is made out of marble. So the marble texture is created using a 3-dimensional turbulence function. So the 3-dimensional turbulence function is used to create or returns an intensity value at each fragment position. And then this intensity value is then passed through a sine function, and this sine function helps to create this sort of veiny marble effect. And then the output of that sine function is then used to interpolate between the 2 different marble colors. So here it's sort of a green and white color. And then we can also add in diffuse and specular lighting to sort of give the marble a shiny effect and make the effect look better. So you can see the bit of shine here. Down here we have a cloudy sky sort of texture, and this was actually created using a 4-dimensional 1 over f noise function or fractal Brownian motion. So the 4 dimensions are the 3 spatial dimensions, and then the 4th dimension is time. And essentially the 1 over f noise function again returns an intensity value at each position, and this intensity value is then used to interpolate between the white and the blue colors to create the cloudy effect. And you can see the sort of cloud formations look as though they're moving and changing with time. And this is because the 4th time dimension is causing the noise, the output of the noise function to change with time, and that creates the nice sort of animated sky effect. Then the final texture here is this molten lava effect. This was implemented using a 4-dimensional turbulence function, again 3 spatial dimensions and the time dimension, to create the animated effect by causing the output to change with time. So similar to with the cloudy sky, the turbulence function outputs an intensity value at each fragment position, and then this intensity value is used to interpolate between the different colors of the molten lava. So you can see it's a nice sort of animated effect here. We can also just zoom in to show you what the textures look like when we zoom in. So we can see the detail as we zoom in, and again the higher level detail that we can zoom in would be created used by the higher frequency, lower amplitude octaves that we've used. So yeah, there you have it. That's my project on Perlin noise.